Hello. Uh, my question is for Preeti sir. As in morning we were going through hardware. Basically, energy. We were saying what would be the various steps to do optimization for power for hardware. So using UPF, we can do the same, right? On RTL level.
Yeah, thank you for raising that. There are a couple of abstraction level differences in the optimizations that we can do for power at the RTL level and the kind of optimizations we are talking about here, which is a little higher at the level of a processor and a system. We talked about memory and the processor pipeline, stages of the processor pipeline where we could do these optimizations. Now, UPF is a format through which you indicate, okay, this can be done, or if there is a clock gating that you would like to do. It is an indication of an optimization. It will be implemented when you indicate the possibility. It will be implemented by the synthesis tool and downstream EDA tools that would that are ultimately generating the design for us. But that is one level of abstraction. What we are talking about, for example, we said that we would do banking on the register file, or we would do banking on the cache. There is an augmented L0 cache that would be added, over and above the regular memory hierarchy. These are design decisions that are not necessarily automated by the EDA tool. These are higher level design decisions that pretty much the designer has to make. And having made that decision of the high level hardware choice, then we can indicate it in certain ways to the synthesis tool and the power optimization tool and so on. But these are different. What we talked about in the morning, that wouldn't be discovered by the synthesis tool or a logic level power optimization tool, because this is a higher level design. Pretty much it is the designer's decision. There also automation is possible, but that's not what we mean when we say through UPF we indicate that this is how you should save power.
Okay, thank you. And continuing on that question, uh, in a perfect world, those solutions will work fine theoretically, but when they are provided onto, because I've heard that low power design is a tough subject. So, what are the challenges which we have to overcome?
Ah, yeah, its implementation is indeed challenging. What we talked about in the morning was essentially restricted to design decisions, right? High level design decisions. And only conceptually we pointed out, okay, that you could monitor things in this way, and you could indicate that, okay, you shut this part of the design off, or you change the clock frequency. This Of course you need to start somewhere, right? So this is more like the starting point. This is the conceptualization of the principle, right? Now, having decided that, there's quite a bit of engineering effort involved in making it work. And not just making it work, there will be many circumstances in which it is not worth it. You will find when you evaluate that it's not really giving you the benefit, because these are general ideas, whereas in particular scenarios, suppose you have decided your application or the domain of applications. When you apply this, you may find that what we are talking about here does not necessarily make a difference for that domain, or it could be that there are some other additional things that are applicable there. So all of those things are there. Some challenges were actually pointed out. We pointed it out, but also through the comments, I noticed that there was one comment that said, when you I think when we were talking about clock gating, there was a question of if you're going to introduce additional logic that will influence the clock period, right? Now, uh, that's an interesting point. There is a, so it points to an important implementation related challenge, which is, yeah, it's nice to say I'll gate the clock, but then if you're going to put logic in the path of the clock, then that's going to affect the clock period. Now, clock period affects every clock cycle in the design. It affects performance. If increasing the clock period, you ought to be very, very careful about doing that, about putting anything in the path of logic that affects the clock period, that might affect the clock period, not just for that particular clock cycle, but all the clock cycles. So these are the engineering challenges. And not that it is not worth it, only thing is it has to be carefully evaluated. So maybe the increment in the clock cycle is small enough that it is worth, but it is a trade-off. There are some things that we are saving as a result of doing these optimizations. There are other things that are costing us. So there is a cost benefit analysis, and ultimately a decision has to be taken. It is a designer's decision of what is it that we are willing to give up by way of performance when it comes to implementing this power optimizations. But indeed, this is one of the cases. Changing the voltage. We said that you change the voltage and you change the frequency and you save power. Again, this is very easy to say, but of course we realize that it is not so easy to actually implement, right? How do you change the voltage and how do you change the frequency? You ought to be able to first generate different frequencies. You ought to be able to, there is some stabilization time as you change from one frequency to another frequency. So there are these implementation details that do not happen in zero time. There is some cost that is associated here too. Because maybe the system is stalled for a short while as you are changing voltage, frequency, or any such drastic change. If we are going to perform, then this costs something. There is some area cost that is associated with dividing a larger. Well, there is area. Well, of course, there is area cost when you want fancy features like this. There is also the other methodological changes that you have to adhere to when you say that I'll run this part of my design at this voltage and that part of my design in that other voltage. What happens when data goes from one part of the one region which is in one voltage to the next to an adjacent region which is operating at a different voltage. So the clock periods are different, and therefore there are some strict design guidelines that have to be followed because these are not independent subsystems. These are interacting subsystems. So yeah, these challenges are indeed there. So what I pointed out are some of the major ones that are known. For specific optimizations, there will be other challenges indeed.
Thank you, sir.
Sure. Any other comments related to the mornings to the power and energy efficiency? Okay, maybe we'll hang around for some more time in case more people join or in case there are other comments.
I have a doubt for Subramanian sir. So you talked about instruction traces, right? What exactly do those traces have? Like we use the pin tool. So what does the trace exactly have?
The trace is nothing but a sequence of addresses. It's just a recording of your program counter as it goes through your entire executes your code. So typically it has just the instructions, addresses that are there. Very often a trace may even have the instruction itself, depending on what the what format or who's generating and for what purpose. Traces also have two things. I mean, they have not only the instruction traces, like for example, if you're doing a move instruction which is moving some data from memory into a register, then it's going to have not only the instruction address, how long the instructions, plus it's also going to have the address of the data and how big the data is which is being transferred. So this sequence of instruction and data addresses is called the trace, and typically most simulators use this in order to run through the entire program rather than rerunning the program every time. We just use the trace to figure out what instruction was running, what address was accessed, right? So,
Sir, in that case, can branch prediction be done properly with this just the memory address?
Of course, you can do branch prediction because for doing branch prediction, see, you are not. Let's assume that you are at a jump instruction of sorts, a branch instruction of sorts. So what you're trying to do is you're trying to predict whether the branch will be taken, not taken, and what will be the target of the branch, right? You're not. The trace already has the truth, right? The trace already knows that what's the next instruction that was taken, but you don't need to rely on that. Your branch predictor will make sure that it uses the it uses the previous information to figure out whether it will be taken, not taken. Of course, the truth is something different. So you will go down the wrong path if it's not
Okay.
taken.
I have two questions for KBS, sir.
Hmm.
Sir, first question is, uh, is there a possibility where we can see that certain instruction is being fetched then decoded in a pipeline manner, and so as to determine what is the pipeline architecture of our processor?
So let me try and repeat the question and see whether I have understood it correctly. What
Okay.
you're trying to ask is, in a real system, in a real processor, can I look to see, what stage of execution an instruction is in? Is that your question, or is
Yes,
your
that is.
question? Okay, that's really challenging. You can't do that for every instruction, and which is why I said you can use something like IBS, an AMD tool, which allows you to trace through one instruction, but not. It uses hardware counters to figure out what really happened to that instruction. But you're not doing it for every instruction. You're doing it for one in, say, a million or so, and getting an idea of what happened to it. That is one way to do. But if you want to really examine how it works, you need a simulator to kind of use a simulator and then go through and see what really is happening down the steps. Does that answer your first question, Anmol?
Yes, sir. And sir, my second question is, in our lab session, we had a particular screen where they were showing us page fault and other things.
Correct.
So, what can we infer from that? As in, there were a lot of page faults, and what we can see from there.
Yeah,
So,
so page faults come in. So what we couldn't show you, and maybe we should, the page fault comes in two variants. There is the major page fault and the minor page fault. Okay, the major page fault typically happens when the page that you are referring to is not in memory, and you need to fetch that from disk to memory. Okay, that's the major page fault. The minor page fault is the page is there, but your TLB doesn't have that mapping. It's more like a this. So that's a minor page fault. It only needs to get remapped. So in such cases, you probably see most of the time in your programs that we gave you those are probably minor page faults that you saw.
Okay, and the first question, you were suggesting some variant of it, as in when I said that, yeah, I am asking that question only. Uh, the
Yeah,
instruction, the
yeah.
execution.
So I told you the instruction execution one, either if you're looking at it at hardware, you need to use IBS. But if you
Okay,
really need to understand how it flows through a pipeline, depending on the pipeline, what's there, you need to probably run it through a simulator. If you want a
okay,
deeper understanding of what is there,
okay,
and you need
understood.
to
Understood.
configure the simulator to mimic, say, I mean, I'm every version of the core that comes out will be very different from the previous. So you probably have to configure the simulator to work exactly like that core.
Okay, understood. Thank you, sir.
There are some questions on the chat. I can take those. One is about security and what is the cost of that. If you want to ensure optimum security at the microarchitecture level, it will be a trade-off with power optimization and overall throughput. Will it always be? Now, power and throughput are different metrics. Um, Security features normally, if no, they would require a constant monitoring in some way or the other, right? Because instructions are flowing through, events are happening, and you have to keep track of what's happening, whether there is something that poses a threat. So you can assume that a power overhead would always be there because there is something active that the security hardware is doing. Throughput, it is not so clear. As long as the design is proper and the security hardware is able to mostly do things, do its checking on its own, it has separate, largely separate accesses to the data structures that it maintains and intervenes only on and off into the rest of the design. Of course, it needs to observe here and there, but what kind of observation it is it the kind of observation that will stall the system and therefore it's for its correct functioning delays are introduced, or is it that it's able to snoop into the system in ways that are not affecting the functioning of the system? These are dependent on the particular kind of security feature. So it's possible that for many of these features, the throughput is not substantially affected. There might be marginal effect. But latency is a different matter. It is possible that that a delay is indeed introduced into the processing of the system. Throughput, which is just the overall rate at which we are able to deliver instructions or results, that might or might not be affected depending on what we are doing as part of the security feature. Power is definitely affected. Throughput, it's possible that it may not be affected. Latency and delays, it will probably be affected because what you are doing, it certainly takes some time, and therefore some delay might be there. It might be hidden from the throughput point of view, but latency might be exposed by security features. That was Nikunj's question. We move to Prithviraj, who asks, how does selection of technology for a particular design affect the power consumption? How should the designer plan keeping these things in mind? Yes, of course, the evolution in technology has everything to do with power, particularly at the lower geometries as we went on from 45 nanometer to 22 and 14 and below 10. The huge difference, of course, was there. The FinFET technology as it was introduced in the 16, 14 nanometer range made a significant difference with respect to the power consumption. Leakage power was significantly different. So the choices, of course, are directly affected. Technological choices, they are affecting, and the reason those choices are made is that there is that power consumption is an issue, and therefore we ought to be doing something about it. The other question is about things like body biasing to manipulate the channel level. Now, yeah, I did not explicitly mention this idea of adaptive body biasing, but it's actually a very interesting technique that changes the characteristic of the transistor in some way because it is influencing the transistors directly. And in fact, there are some changes, maybe it's the threshold voltage that changes, ultimately leading to a difference in the dynamic power and the leakage power of the transistors. So yes, we said early on that there are a fixed set of tools, as it were, at the logic level and at the technology level that we manipulate at the higher level. So for the processor and a system is kind of a higher level of abstraction, but the tools that are available to us are the same, which is clock gating, power gating, where we shut off power, clock gating, where we don't allow toggling of the clock, frequency changes, voltage changes. These are, of course, the standard mechanisms. At the lower level, these are the mechanisms that we would use. The intelligence at the higher level is how do you coordinate? When do you take things down to sleep? When do you decide the voltage transition? These are the questions that you need to ask. But to add to that, what's pointed out here is this idea of adaptive body biasing that changes the characteristics of the transistor itself and therefore also changes our power consumption profile. So you could add this to the list of things that we are doing, like the clock gating mechanism and like the voltage scaling mechanism. And indeed, at least at the research level and several implementations, this idea of dynamically changing the biasing of the transistors so that you get the power optimization effect that you want. That's indeed that has indeed been tried out successfully. Now, it does have to translate all the way into a methodology. So something like clock gating, this is something that is well understood for decades now, and therefore you see that the design tools that are available for us, right? The synthesis and the power optimization tools, they have already captured, they have already integrated these features and to the level where you say that, okay, perform clock gating on this kind of data, and it would. So some of the flip-flops we would then be changing into clock-gated flip-flops. Now, body biasing, does it stand at the same level? I actually don't know. This is a more sophisticated optimization, but one would imagine it would have to proceed along the same lines. That is, you would need the ability to control. That has to be provided at the technology level. Once it is there, then a design automation tool or even the designer manually or automatically, we decide that, okay, now we change the characteristics, now we bias it this way, or now we change these settings. So finally we need it in order to apply it at the architecture level. We need a simplified control that says now you change the state from this mode to that mode. That's what you would need to implement such a thing at the high level. But whether the tools, EDA tools now are specifically handling body biasing, I actually don't know. If somebody is aware, they can share. But the methodology would be similar to the way we handle clock gating or voltage scaling or any of the other knobs with which we control power optimization. Okay, let me stop here. If there are other questions, feel free to communicate. There's one question that says, when we say power optimization, it is required from analog circuit design level to digital system to system level runtime scheduler. What is the exact gap? Um, Not very sure I understood this properly. Um, there is analog circuit indeed that is involved here, because ultimately, let's say I want to change the voltage level from one level to the other. Of course, these are analog circuits ultimately that perform the frequency change for us. The level at which we discuss this optimization, the controlling decision is taken at the high level. So these are digital levels at which the decision is taken, but the implementation is through analog circuit indeed. But I'm not sure I missed something else in this though.
Sir,
Yeah.
building on that question which has been asked, what I would like to ask is, if we would have to consider a certain power amount of savings is being done at a certain level, uh,
Yeah.
what amount of as in if we can put it in a decreasing order, how much power is saved in each level, can be saved at each level, be it circuit level, system level, and let's say at OS.
Okay, so there is a general um, understanding that the opportunity for power optimization uh, becomes higher at higher levels of abstraction. Opportunity, I mean, this is a sort of a vague, let me define it properly. Now, of course, to implement the power optimization, you do need to go down to the lower levels, right? All the way to the circuit level. Now, but the thing is that you could think of it as some kind of a superset that is available to us as we go up the level of abstraction. So let me take an example. Suppose it is at the level of a processor where we decide that, okay, this particular, let's say I have an 8 processor core system, and I look at the idle time profile of my different cores, and I take that decision that okay, since this particular core seems to be idle, it is not doing much work over a period of time, let me shut down that core or take it to a deep sleep kind of mode. This decision is taken at a high level, right? This decision is usually not something that we usually take at the level of a circuit, whether it is an analog circuit or some small circuit. This is really at a very high level, and it's actually suitable for as an operating system decision making, because that's the controller that has visibility into the entire system. It is able to monitor what all the processors are doing if there are 8 of them, and is able to take this decision. In fact, we'll talk more about it when we talk about the server space next week. But here's one important decision that really is in the domain of the operating system, where I see that I have 8 processors in my system, and yet the amount of work they are currently doing together amounts to only, something that 4 of them can do, and the other 4 I can take down into a sleep state. Not that they are not doing anything, but just if I look at the amount of work they are all doing together, I could actually shift all the workload into half the processors and shut down the other half of the processor. This is something that only an OS could have done. A low-level circuit would not be able to do this, because that much information about the whole system is not available. So yes, in some, so this is an example of that general principle that as you go higher, you the opportunity for optimizing on power increases. It's not that it is quantified in some explicit way, but the opportunity does increase because you have a greater visibility into the system, into the different parts of the system. At a lower level, you don't have that visibility, but at a higher level, you do that. So as you keep increasing the number of modules that are interacting with each other. So let's say these are several ALUs, and then it goes up to one full processor core, then it goes to multiple processors, and so on. As you go up the chain, you will typically find more opportunity for optimization.
Oh, thank you, sir. That was helpful.
Okay.
Kenny, sir, you said you would share a paper studying a real world problem being solved by lab members.
I'll do that. I'll do that. I'll do that. I'll put it on the files in the perf lab.
I actually have this confusion. Like, what are the steps, like step by step process that we should go? For example, just a case like
Yeah. Please ask.
just like a case of matrix multiplication of A and B, we have this algorithm where we can split A into the multiple rows and B into multiple columns and then multiply and get some boxes. Those kinds of operations we can do, but we don't know what exactly, how exactly it is mapped to the hardware. So we have to, I don't know what are the exact steps we should.
Yeah, so that's why you have these tools, these optimization tools. You have to, in order to first, before you run the optimization tools, you first have to probably, if you suspect that from an algorithmic standpoint you're doing well, and you're not sure that the problem is with the mapping to the hardware, then a good thing would be to run these tools like perf, which will tell you whether there is a bottleneck existing in terms of caching, the way you're using the cache or not. So we'll have to run through a few things like that. The paper will not talk to you about this because the paper talks very specifically about a more modern workload and analyzing that. This one, typically there are good software optimization guides which you will find, which will tell you how to optimize your code for a particular architecture. There's some general kinds of things which you can do, and there's also some specific kind of optimizations that you can do. Many of the optimizations inherently your compiler will do for you. You have to turn on those compiler optimizations. That's probably the compiler optimizations itself is probably good for a lecture by itself. So I'm not sure we can cover it in this short discussion.